Welcome to session 4, where we will be looking at the molar volume of gases. By the end of the session, you should know that the molar volume is the volume occupied by 1 mole of any gas at a certain temperature and pressure. And also that the molar volume is the same for all gases at a fixed temperature and pressure. And you should be able to carry out calculations involving the volume of gas, molar volume, number of moles of a substance. Before we start looking at molar volume, it's important to remind ourselves, what is a mole? And in chemistry, we're not talking about the furry wee creature that burrows under the ground and makes these mounds of earth. For chemists, the mole represents a number. So in the same way that a couple is 2, a dozen is 12. So a mole also represents a number. It's just a very big number. Atoms, molecules are so tiny that it makes no sense to deal in 1 or 2 or 3 of them. We have to group them together, and we use our relative atomic masses to express the mass of 1 mole of the elements. So for carbon, the mass of 1 mole is 12 grams, and within that 12 grams of carbon, there are 6.02 times 10 to the 23 atoms of carbon. So the mole is just a word to represent a set number of atoms or molecules. Just the same way as a couple means 2, a dozen means 12, a mole represents a fixed number of atoms or molecules. So the molar volume is the volume of 1 mole of gas. And when we're looking at molar volume, we always give a temperature and pressure. This is because gases expand or contract depending on the temperature or pressure around them. So we have a balloon filled with gas here, but if we increase the temperature, we find that the balloon will increase in size because the gas inside is expanding. Similarly, if we decrease the temperature, the balloon will get smaller in size because the gas inside is contracting. And why does that happen? Well, we know at higher temperatures, particles have more energy, so the gas particles are bouncing around, hitting off the edges of this balloon and pushing the sides outwards. Whereas at a lower temperature, they have less energy and they're putting less force on the edges of the balloon and it contracts in. We'll consider changes in pressure now. Firstly, an increase in pressure. When an external pressure is applied, the pressure pushes on the sides of the balloon, causing the volume to decrease. We've still got the same number of particles there, they're just closer together. When the pressure is reduced, the gas expands and the volume increases. Still the same number of particles, they're just further apart. So these changes are why we need to make sure we know the temperature and pressure at which we're working, because the molar volume will vary depending on the temperature and pressure. So it doesn't matter whether we've got elements or even compounds. If we have the same volume, we have the same number of moles. So molar volume is the volume occupied by 1 mole of gas, and it doesn't matter what the gas is, 1 mole, same volume. And we could have the same volume and same number of moles. So at normal room temperature and pressure, the volume of 1 mole of gas is typically 24 litres. So if 1 mole is occupying 24 litres of space, of volume, then if I've only 12 litres of gas, I only have half a mole. We have an equation that links the volume of a gas, which we measure in litres, to the number of moles, and we'll tie that in with the molar volume, the volume per mole, and that is in litres per mole, and you'll see it written in either of these ways. There are 4 types of question based on molar volume. We're going to look at each in turn. The first one we'll look at is the one that comes up most often. So the basis of this type of question is that they'll tell you how much of the reactants there are, mass, or concentration and volumes, and they want to know how much product will be made, but they want the volume of a gas. So in this question, methanol can be used as a fuel in a variety of different ways. An increasingly common use for methanol is an additive in petrol. Methanol has been tested as an additive in petrol at 118 grams per litre of fuel. Calculate the volume of carbon dioxide in litres that would be released by combustion of 118 grams of methanol. Take the molar volume of carbon dioxide to be 24 litres per mole. So our first step, as is often the case, is calculating moles. We have a mass of methanol. We've got our formula for methanol, so we can get our gram formula mass. From that we can calculate moles. And you'll see, as I've done in the past, I've highlighted the information relating to methanol, and I've highlighted in a different colour information relating to carbon dioxide, just to help me be clear with what belongs with what in the calculation. So substituting in our numbers, we have 3.69 moles of methanol. I've rounded on the page to 3 sig figs because the mass of methanol was given to 3 sig figs. I have not rounded in my calculator. You should never round in your calculator until the final step. Keep the number in your calculator. Our second step, we are going to use our balanced equation to compare the mole ratios of methanol to carbon dioxide to allow us to calculate the moles of carbon dioxide from the moles of methanol. Now the mole ratio from the balanced equation is 2 to 2, which of course simplifies to 1 to 1. So if we've got 3.69 moles of methanol, we should, in an ideal world, produce 3.69 moles of carbon dioxide. Now this might seem fairly self-explanatory because it's a 1 to 1 mole ratio. You must show you're working. You must show the examiner that you understand that it's a 1 to 1 mole ratio. For the final step, we will use the moles of carbon dioxide we calculated and our molar volume equation to work out what volume in litres of carbon dioxide there is. So I've rearranged the equation so that I've got volume of gas as moles times molar volume, and that gives me 88.5 litres. Now if we had rounded over in step 1 and step 2, and we used this rounded number instead of the longer number in the calculator, we would actually get an answer of 88.6, which would be marked wrong. So although you might round on your page, never round on your calculator until the last final step. If you're struggling to remember the equation, just take your time and think it through, because you can get it a different way as well. If 1 mole of gas is 24 litres, then 3.69 moles is 24 times 3.69, which gets us to our 88.5 litres as well. So you can work it out using just proportions, or if you remember the equation, you can get the answers that way. So marks in this question, there was 1 mark for calculating the moles of methanol to begin with, and the second mark is for doing the molar volume calculation, and you must have the proportions correct in the middle to get the answer right in step 3 here. Phosphine is used as an insecticide in the storage of grain. Phosphine can be produced by the reaction of water with aluminium phosphide, and we have our balanced equation there. So 2.9 2.9 kilograms of aluminium phosphide were used in the phosphine generator. Calculate the volume of phosphine gas in litres that would have been produced. Take the volume of 1 mole of phosphine to be 24 litres. We're going to use the same 3 steps as last time. We're going to calculate moles. We're going to look at proportions, the mole ratio and the balanced equation. And then finally, we're going to calculate our volume of gas. The only thing to watch here is converting the kilograms into grams. And dividing through, we get exactly 50. So I'm not worrying about sig figs just now because it was 50 dead on. On to step 2, where we're looking at the mole ratio in our balanced equation, and it's 1 to 1. That doesn't mean we miss out the step showing the working. We still write it down, but it does make our calculation easier. So the final step is calculating the volume of gas using our molar volume equation. So that gives us an answer of 1200 litres. Again, if you prefer using the proportions, you can be saying, well, 1 mole of gas is 24 litres, so 50 moles is 24 times 50, which gives us the same answer of 1200 litres. So again, a 2-mark question. First mark is for your mole calculation, and the second mark is for working through and getting the correct volume of gas at the end. This second type of question comes up in multi-choice, and it's playing on the fact that the same temperature and pressure, equal volumes of gas will have equal number of moles. So we have copper oxide reacting with ammonia to make copper, nitrogen and water. And it wants to know what volume of gas would be obtained from the reaction of 100 centimetres cubed of ammonia gas and excess copper oxide. All volumes are measured at atmospheric pressure and 20 degrees Celsius. So some things we can rule out from this equation straight away, because we're talking about gases, and it's only gases where equal volumes are equal moles. So we're going to just cross out everything in the equation that won't be a gas at 20 degrees Celsius and atmospheric pressure. Copper oxide is a solid. Copper, metal, a solid. Water will be a liquid at 20 degrees Celsius. So that leaves us with 2 things to home in on, the ammonia and nitrogen. And that's much simpler for us now. Our mole ratio, ammonia to nitrogen, is 2 to 1. So for every 1 mole I have of ammonia, I'll have half a mole of nitrogen. So that means the volume of nitrogen will be half as much as the volume of ammonia. I've got 100 centimetres cubed of the ammonia, so I should make half of that 50 centimetres cubed of the nitrogen. And that means answer A is the correct answer. Whenever you're tackling multi-choice, if at all possible, try and answer the question without looking at the choices, the A, B, C, D. They're there to distract you, most of those answers. There's only one right, the rest are distractors. So try and answer the question before looking at the possibilities so you avoid being distracted. This question is a similar type to the last, but it's also bringing in the idea of excess. With 100 centimetres cubed of propane, 600 centimetres cubed of oxygen, and mixture is ignited. At the end of the reaction, total volume of gas would be, like I said with the last example, try not to look at these. Try and work through the question without looking at the possible answers. Straight away we can rule out the water because it is a liquid, so it's not going to be involved in the volume of gas at the end of the reaction. And then we have to look at our propane and oxygen and decide which is in excess and which is limiting. So from our mole ratio in the equation, we know that propane reacts with oxygen in ratio of 1 to 5. It says we have 100 centimetres cubed of propane. So for all that propane to react, we'll need 500 centimetres cubed of oxygen. Going back to the question, it says there's 600 centimetres cubed of oxygen. So we have 600 centimetres cubed of the oxygen. We need 500 centimetres cubed. So left over, we have 100 centimetres cubed. That doesn't react. We're assuming this is in a closed vessel. So there's going to be that 100 centimetres cubed left over at the end that hasn't reacted, along with any product that is produced. Now we know that the propane is limiting what's made. We're going to compare the propane with the carbon dioxide, because it's the one that's limiting how much carbon dioxide we can make. So our mole ratio there is 1 to 3. And if I have 100 centimetres cubed as the propane, I should be able to make 300 centimetres cubed of the carbon dioxide. Same temperature, same pressure. 1 mole of propane would take up the same volume as 1 mole of carbon dioxide, but I have 3 times as much carbon dioxide, so it's 3 times the volume. So looking up at this balanced equation, I've put the information we've worked out there. The propane was limiting, all of it was used up in the reaction. We had excess of 100 centimetres cubed for the oxygen, and the propane reacted to make 300 centimetres cubed of carbon dioxide. So we've got the carbon dioxide that's produced together with the leftover oxygen, giving us a total of 400 centimetres cubed of gas left over at the end. So the end of the reaction, total volume of gas would be 400 centimetres cubed. And that gives us answer B as the correct answer. This third type of question is really testing whether you understand the concept of the molar volume of gas or not. It's saying, under the same conditions of temperature and pressure, which of the following gases would occupy the largest volume. Now the temptation here is to start calculating volumes with the volume of gas is equal to moles times the molar volume. But at a fixed temperature and pressure, the same number of moles will be the same volume. Or you could look at it in terms of, to get the volume of gas, you're multiplying the moles by the molar volume. And the molar volume is a constant for a set temperature and pressure. If we're talking about room temperature, it's 24 litres per mole. If we're talking about standard temperature and pressure, or 22.4 litres per mole, it's a constant that we can link to pressure and temperature. So each moles is going to be multiplied by the molar volume. So why bother? What you really need to focus in on is the number of moles. The bigger the moles, the bigger the volume. So what they're really asking you to calculate here is which of these gases has the highest number of moles. So carrying out a few quick mole calculations, we can see that there's the greatest number of moles of hydrogen. So answer A is the correct answer. So this is another question of the same type. Which of the following gas samples has the same volume as 4.0 grams of methane? Same volume means same moles. So our first step here, if we want to have the same volume as methane, we need the same moles. So we need to know how many moles of methane we have. So that's going to be our first step. So we have 0.25 moles of methane. We now need to go to the other possibilities given and see which of them has 0.25 moles as well. If it is 0.25 moles, it will be the same volume as methane. Same moles, same volume. So calculating out these moles, we can see that helium, our first one, is 0.25 moles. It matches the methane. Now you must remember your diatomic elements. If you don't remember these are diatomic, you'll get the wrong gram formula mass, and then you'll get the wrong moles, which means you won't get the right answer. So you must remember your diatomic elements. So the answer to this one, helium, A, 1 gram of helium is the same volume as 4 grams of methane. The fourth type of question you might get is one of the open-ended questions asking how to find the molar volume. And here we are, 2018, question 10. The molar volume in units of litres per mole is the same for all gases at the same temperature and pressure. Using your knowledge of chemistry, suggest how the molar volume of gases could be measured and compared. Any suitable chemicals and apparatus can be used. Some suggested chemicals and apparatus are given below, and we've got a whole list of things there. Now, while this question is focused on molar volume of gases, there's some things you should always bear in mind when you're going to answer an open-ended question. These questions are a chance for you to show off your chemistry. And so you should always be trying to get in these things. Now, this isn't an exhaustive list, but getting in some of these things will ensure you are shown you have a good knowledge of chemistry. Can you put in balanced chemical equations? Can you put in structures? Can you put in a diagram of apparatus and label it? Can you describe how to carry out a calculation? So not just putting in equation you've copied out from the first page of the data booklet, but how you would use that equation. Now, these won't apply to every open-ended question that you get, but you can usually get at least 2 of them in. So looking over here, how do we calculate a molar volume? Well, the volume of 1 mole of gas, if we know how much of a chemical is reacting, we know the moles of gas we expect, and we can measure the volume of gas produced, we can link the moles to the volume. Here's an example of equipment that I've used with students before to measure molar volume of gases. And I'm hoping it shows up okay on the video here. It looks quite complicated, but I'm going to talk you through the different parts of it. Down here in the test tube, we had metal. We were using magnesium in this experiment because magnesium reacts with acid to produce hydrogen gas. So at the start of the experiment, there was an accurately measured mass of magnesium, and the magnesium had been sanded down to make sure we'd removed any layers of magnesium oxide from the surface. Up at the top we have a thistle funnel where we put the acid, and the acid was separated from the magnesium by a little tap here. Then we had a delivery tube down into the test tube and another delivery tube coming out, and any gas produced would go along this delivery tube to be collected in the gas syringe. So essentially we've got acid reacting with metal to produce hydrogen gas, and it was collected here. Something else that reacts with acid are metal carbonates. So you could run this same experiment with a known mass, accurately measured mass of a metal carbonate, excess acid in the thistle funnel, open the tap, the acid drops down, you close the tap to make sure the gas doesn't escape back up this funnel, and any gas produced is collected in the syringe. So from a known mass, which we can then calculate moles, we know how many moles of gas should be produced, and we have a volume linked into that number of moles. So if I was answering this question, I would start with an equation for a reaction, showing magnesium reacting with hydrochloric acid to produce hydrogen gas. I've got my ballast equation here. And then I would be saying, well, if I know my moles of magnesium, I know how many moles of hydrogen should be produced. So in the experiment, I can measure the volume of hydrogen, I know the moles of hydrogen I should have, and from those two I can then scale up and say, if X many moles gives this volume, then 1 mole will be this volume. I could then draw a diagram using some of the apparatus here. I've weighed out my magnesium. Here's a rough sketch of the apparatus I showed you in the photo. Things to be careful with when you're drawing stoppers in. Now, ideally you'll have done this with a ruler and a pencil and it'll be beautifully neat and your lines will be straight. It's not so easy for me to do this on the screen, but yours will be beautiful, I'm sure. When you're drawing in stoppers, make sure the edges are sealed. When you're drawing the end of a gas syringe, make sure the ends are sealed. Make sure the delivery tubes are sealed. You're drawing this as if you've cut the apparatus in two. 2 questions that will be in the marker's head. Is it safe? Does it work? If there's little gaps in your tubing, it won't work because gas would escape, so that's no use. Now in the open-ended questions, they're probably not going to be quite as strict in that as if it was a question about drawing apparatus. But it is good practice to make sure you're paying attention to that any time you draw apparatus. So I would be accompanying the sketch with a description of the experiment and then how you would relate the volume of hydrogen you collected to the number of moles of hydrogen, which you've got from the mass of magnesium, to get a volume for 1 mole of hydrogen gas. There's a lot of knowledge of chemistry there. You're showing you know that metals reactive metals react with the acid to give you hydrogen gas. You're linking moles of your reactant to moles of your product. You've got labelled apparatus, and then you've got the connection to the molar volume as well. The other way you can get molar volume is you get a flask of known volume, and you get a stopper, delivery tube, and it has to have some sort of tap here. And you connect this up to a vacuum pump, and you suck all the air out that's inside it. Once you've done that, you seal the tap and you weigh everything on a balance. And here's where the balance and cork ring would come in. You would sit the flask on the cork ring and sit all of that on the balance and get the mass for that. Then you can connect up a cylinder of gas, carbon dioxide, nitrogen, hydrogen. Connect up the cylinder of gas and you fill the flask with the gas, and you keep going, just keep filling till no more will go in. And again, you seal the tap. And you weigh the flask again. And the mass of the flask will have increased because of the gas in it. So you've weighed the flask when you've used a vacuum pump to empty it. You then weigh the flask when it's filled with the gas. And you see the difference in mass. You know the volume of flask. You now know the mass of gas. You can convert the mass to moles. So you're linking the moles to the mass of gas. The difficulty with this method is that gases are so very, very light, it's difficult to get a balance accurate enough to give you a good reading. But it is a method that's used. The Hodder-Gibson textbook has a much nicer diagram of this and a very clear explanation of the experiment, so look it up. I'm not going to give you a page reference because the different editions will be slightly different pages. The section is calculations involving gases. So hopefully you understand now that the molar volume is the volume occupied by 1 mole of any gas at a certain temperature and pressure. You should also know that the molar volume is the same for all gases. Doesn't matter if it's nitrogen, methane, carbon dioxide. At fixed temperature and pressure, it's the same for all gases. And we've looked at examples of calculations and questions based around volume of gas and molar volume and number of moles of a substance. There'll be questions for you to try. As always, if anything isn't clear or you want some further explanation or you want us to go over certain questions, just fill in the form, the Microsoft form, and we'll do our best to cover it in the live webinar.